Okay, 2012 AMC. This was problem 19 from AMC12A and the problem 23 from the AMC10A. And it says Adam, Benin, Xiang, Deshawn, Esther, and Fiona have internet accounts. It doesn't matter their names, so we're not going to call them. Let's call them A. Oh, I guess I didn't even notice that. Yes, that is wonderful. Some, but not all of them, are internet friends with each other, and none of them has an internet friend outside the group. So there's an important point here that I missed the first time I looked through it, and I didn't see my answer in here, so obviously I checked and I saw it. Some, but not all. We'll get back to that. Okay. Internet friends with each other, and none of them has an internet friend outside the group. Each of them has the same number of internet friends. In how many different ways can this happen? Okay, first thing, I look at this as a graph, and that's where, so a graph of 6 vertices, A, B, C, D, E, okay, so A, B, C, D, E. And, F. Okay, so in here, now we know from some graph theory that the number of edges is going to be 6 choose 2. Not that important for us, okay? It's 15 edges. I'll draw them in because I'm going to use them to explain some things, but each vertex has degree 5, possibly in the complete graph, but of course there's a part of this that says we can't have a complete graph, and we'll talk about that. Okay. I think I got them all. Alright, so here's the idea. Some, but not all. So let's look at this. So let's call this the number of friends. So friends, and the number of, and this will count the number of ways I can do that. So first off, 0 friends we don't care about. They have to have some friends. We'll go through 1, 2, 3, 4, but 5. If they are each friends with 5 other people, that means all of them, so we're not going to care about 5 either. And that doesn't make much of a difference. There's only one way to have 0 and one way to have 5, so it's a real easy case, but they threw it out anyway. Okay, next. The number of ways to have one friend. Okay, so the only way we can have one friend is if I have pairs. So, for instance, A and B can be friends, but then they can't be friends with anyone else. But I still need to have friends for this. So C and D could be friends, and they can't be friends with anyone else. And E and F can be friends, but then they can't be friends with anyone else. So that's the only way. I mean, I could have then A and D, and so, but 3 pairs is the only way to get this to work out. So let's figure out how to count that. Okay, and the way that I did that is we'll always start with A. Or let's say, for my first group, I have 6 times 5 ways to choose that. But order doesn't matter. For my second group, I've already chosen 2 people to be in the first group, so I have 4 times 3 ways to choose that, but again, order doesn't matter, so I divide out 2 from there. And for the last group, I have 2 times 1. Now actually, once I've chosen the first 2 groups, first 2 pairs, there's no choice left. I'm stuck with this. And there's one more problem. So this, and this, there's an ordering implied to this, saying this is my first group, this is my second group, this is my third group. But if I switch groups, so let's say I chose C and D first, then A and B, it's the same way that we can have friends, so I need to divide that out by 3 factorial, which is the number of ways that I can arrange my 3 pairs. So let's see, let's just do a little bit of math here. Computation, it's not really math. So it's going to be, okay, so that is 15, 6 times 5 divided by 2, times 6 times 1 divided by 6, which is 15, okay? And a thing that's going to be useful to see is the way we can have people with 1 friend is the same way that we have people with 4 friends. So this will also be 15 different ways. And the reason is this. If I count the ways that I can have 1 friend, that's the same way as saying that counting the ways that I have 1 anti-friend, not friend. So if I said that A and B were friends, that's really the same as saying that A is friends with everyone except for B, and B is friends with everyone except for A. It's the same number of countings for that. Okay, 15 and 15. First step done. Second step, which tripped me up for a little bit, is 2. And for the same reason, we'll count 3 the same way. But then I noticed, okay, well, let's just start looking at this. And first choice, if I have A friends with E, friends with C, okay, I cannot have C be friends with B and not go all the way around the loop, because I can't have a length 4. So I have to either close it off here or go the rest of the way around the loop. So let me show that. So if I have this as one connection, notice each person, A has 2 friends, E and C, E has 2 friends, and then I have the same thing going on here. Okay, they all have 2 friends apiece. It fits up, it works out. The other possible choice is to have it going all the way around, and notice each vertex in my yellow subgraph has degree 2, so each person has 2 friends. But I cannot just have a pair, obviously. I cannot have a group of 4, because then what's going to happen here? I can't connect them up. That would be too many friends, and these don't have the right number, and for the same reason I can't have a group of 5. Okay, so let's look at this. First, the number of ways that I can connect up 3, and that means I'll also connect up these 3, is going to be 6 choose 3. That's the way I can choose one group of 3 and one group of not 3. But again, if I choose this group of 3 and then that group of 3 is implied, it's the same thing as choosing this group of 3 and then the other group of 3 is implied, so I have to divide this by 2. So 6 choose 3, that's going to be 6 times 5 times 4. The 3, 2, 1 cancel out once, divided by 3 times 2 times 1. 20 divided by 2 is 10. The other way now, so 10 ways to have groups of 3. Ways to have paths or groups of where I have one big cycle going around there is going to be 6 factorial for ordering this. So 6 factorial for ordering that. But then, if I rotate it, let me write it this way. Let's just start my cycle at A, and that means I have only 5 factorial left. I could have divided out the 6 and gone there. But if I go, let's just say A, B, C, D, E, F back to A, that's the same as going as A, F, E, D, C, B back to A. So I divide this by 2. 5 factorial is 120 divided by 2 is 60. So these together give me 70, but as before, the way to have 2 friends is the same way as not having 2 friends, same number of countings, so these are the same, so this one also equals 70, and so I end up having, in the end, finally, we have 15 ways to have 1 friend, 70 ways to have 2 friends, 70 ways to have 3 friends, and 15 ways to have 4 friends, which adds up to 170 ways to have some, but not all, of them as friends in the same number.